Alright, welcome back everyone. Today we're going to cover another theorem that can help you solve some geometry problems in the AMC and other contests. This theorem is called Ceva's theorem. It states that if you have any triangle ABC and you have three line segments AD, BE, and CF that all meet at the same point, here notated as O, then the following equation holds. AF over FB times BD over DC times CE over EA is equal to 1. So this equation holds no matter what shape triangle ABC is in, no matter where the interior point is, as long as these three line segments meet at the same point, this equation is always true. Alright, so now I'm going to go ahead and prove this theorem. So first off, let's look at the line segment AB. So something that we can take note of is if we have a triangle as such, and we have a line like this, then the two areas AB and the two line segments XY over here are related. Essentially, the ratio A to B is equal to X to Y. And the reason is, if I draw the height of this triangle, we see that first we're going to prove this result. If we have a triangle as such, and I draw this line like so, then we have a relation between the areas of these smaller triangles and the length of their bases. The relation is A to B is equal to X to Y. And it's relatively easy to prove this. If I draw the height down here, and let's say the height is H, then we have that the area A is equal to half XH, and the area B is equal to half YH. And therefore, A over B is equal to half XH over half YH, and the half H's cancel out, and so A over B is equal to X over Y. In other words, A to B is equal to X to Y. Okay, we're going to prove another related result. If I draw a triangle here, and let it be ABC, and I draw from C a line segment to AB and call this point D, and we mark out an interior point on line segment CD and connect E to A and B. So this is our diagram, and the result is that the area of triangle ACE divided by the area of triangle BCE is equal to the ratio AD over BD. And this is actually relatively simple, because we can note here that by the previous theorem, the area of triangle ADC divided by the triangle of BDC is equal to the ratio AD over BD, because the triangle ADC being this one and the triangle BDC being this one, they share the same base, which is AB, and so the ratio of the areas is the ratio of their respective bases. And again, we can look at triangle ADE and triangle BDE, and the same result follows. So we have that the area of triangle ADE divided by the area of triangle BDE is also equal to AD to BD. So now we have these equations down here. And we're going to use these by simply saying, okay, if this ratio here and this ratio here are equal to the middle ratio, then the difference of these two ratios is also equal to the middle ratio. And that, if we write it out, would be the area of ADC minus the area of ADE divided by the area of BDC minus the area of BDE. And it's equal to the middle ratio, which is AD over BD. Okay? And now it's really easy to see because the area of ADC minus the area of ADE is simply the area of ACE. And similarly, the area of BDC minus the area of BDE is equal to the area of BCE. And so this theorem is proved as well. Now we can move on to the proof of the original theorem, Ceva's theorem. Okay, so considering the last theorem that we proved, we can write that the ratio AOC over the area of BOC is equal to AF over FB. But we can also write this for the other two sides. So, for example, we can write BAO over CAO is equal to BD over DC. And lastly, we can write that the area of CBO over the area of ABO is equal to CE over EA. Now finally, we can multiply all of these ratios on the right-hand side and see what we get. So we have AF over FB times BD over DC times CE over EA, and we want to show that this is equal to 1. Well, that would be relatively simple, because if we simply label these three areas as, let's call it X, Y, and Z, then we have that AF over FB is equal to big X over big Y, and BD over DC is simply big Z over big X, and CE over EA is simply big Y over big Z. And all of these values cancel out, and we get 1 as our result. So this proves Ceva's theorem. Now the reverse of Ceva's theorem is also true. Namely, if I have shown by other means that in a triangle ABC with points D, E, and F as such, and I have shown by other means that AF over FB times BD over DC times CE over EA is equal to 1, then I can assume that, then I can say that AD, BE, and CF meet at the same point. So note that the theorem that we've proven is the other way around, namely that if we have the three line segments meeting at the same point, then this equation is true. But we can also show that the other way around is also true. So essentially we have here one statement, and here it's an equation, and another statement. And this theorem is true so that if one of these statements is true, then the other one is true as well. Now the reverse version of Ceva's theorem can also be proven relatively easily. So I'm going to draw another diagram here. but we're going to try to prove that the line segments AD, BE, and CF pass through the same point. But we are given that AF over FB times BD over DC times CE over EA is equal to 1. We need to prove that they meet at the same point. And one good way to prove this is by saying, okay, let's say that the line segments AD and BE meet at a point called O. And let's draw a line segment from C through O down onto the line segment AB, and let's call this point F prime. We're going to try to show that F prime and F are actually the same point. If they are the same point, then CF has to pass through the intersection of AD and BE. Now, by the forward Ceva's theorem, we know that since AD, BE, and CF prime pass through the same point O, the equation AF prime over F prime B times BD over DC times CE over EA is equal to 1. And we have proven by other means, or we are given, that this first equation is true. We know by the forward version of Ceva's theorem that the second equation is true, and therefore we can conclude that AF over FB is equal to AF prime over F prime B. Now when you think about this equation carefully, you'll realize that there is only one point P between A and B that have this ratio. And that means that F prime and F must be the same point. And since they are the same point, that means that CF must pass through the intersection of AD and BE, and so the three lines meet at the same point. And that proves the reverse version of Ceva's theorem. Okay, so here's Ceva's theorem, and if you want to take another look at it, you can pause the video here. Okay, next we're going to move on to an example. Okay, so suppose all of these values are given, and you know that the three line segments AD, B, and CF pass through the same point, O, and you're asked to find what AE is. This example is obviously really easy. The contest problems aren't going to be as straightforward as this one, but I'm going to use this as an opportunity to introduce a very easy method to memorize Ceva's theorem. Essentially what you do is you can start at any vertex. I'm going to start at vertex A, and we're just going to go counterclockwise with all of the values until we go back to A. So first, the first value that we encounter is 5, the next one is 7, and the next one is 8, the next one is 4, and then it's 4, and the final one is AE. We don't know what AE is, so I'm going to leave it as such. So that was really quick, and now you have Ceva's theorem all stated by equating it to 1. So now all you have to do is solve for what AE is. Well, if you go ahead and solve that, you will see that AE is equal to 40 over 7. So there you go. This is Ceva's theorem and how you can apply it. Thank you for watching, and I'll see you next time.